Definition. Subgroup H of a group G is called a normal subgroup of G if the left coset H is equal to the right coset HA for all A in G. And this is how we denote that H is a normal subgroup of G. This equality is equivalent to the following. Multiply both sides by the inverse of A to the left, and we'll get H equals A to the negative 1, HA for all A in G. So it is equivalent definition for a normal subgroup. It is very convenient to prove that a given subgroup of a group is normal using this theorem called normal subgroup test. A subgroup H of G is normal in G if and only if x to the negative 1 is a subset of H for all x in G. The proof is pretty easy. We just prove that the left coset and the right coset with representative A are equal by proving these opposite inclusions. Example 1. Every subgroup of an abelian group is normal, and this is because any two elements commute, so H is equal to HA, which means that the left coset A times the subgroup H is equal to the right coset H times A. Similarly, in any group, the center of the group is normal because, again, the elements from the center commute with any element in the group. Another example, the alternating group AN of even permutation is a normal subgroup of Sn. And this is because if we apply the normal subgroup test, then x to the negative 1 will have the same type, even odd type, as A. And the reason for this is because x and the inverse of x are both even or both odd permutations. Example 7. If a group G has a unique subgroup H of some finite order, then H is normal in G. To see this, observe that for any G in G, G to the negative 1 is a subgroup of G. This can be checked easily using the subgroup test. And then those two groups have the same order, which means that because H is unique group of a subgroup of that order, this G to the negative 1 must be equal to H, and that is even more than the subgroup test, the normal subgroup test requires. There we want inclusion, and here we get even equality for any G in G. g to the negative 1 must be equal to h. Example 8. The group SL2R of 2 by 2 matrix with determinant 1 is a normal subgroup of GL2R, the group of 2 by 2 matrices with non-zero determinant. Here in both groups the multiplication is usual multiplication of matrices, a row times a column, dot product. To verify this that the special linear group is a normal subgroup of the general linear group, we apply the normal subgroup test. And select X in GL2R, H in SL2R, then consider the products of H and X are matrices. X to the negative 1 has determinant equal to the determinant of X times the determinant of H times the determinant of X to the negative 1. We know this from linear algebra. Determinant of a product is product of determinants. But the determinant of H is equal to 1. And we know this from here. So this can be replaced with 1. We get this. And a number times its reciprocal, of course the product is 1. This means that the determinant of this matrix is 1, so that matrix must be in H by definition. Therefore, for any H, this matrix is in the subgroup H, which means this set is a subset of H. And this is the requirement of the normal subgroup test. So, the special linear group is a normal subgroup of the general linear group. Factor groups. When the subgroup H of group G is normal, then we can construct a new group called factor group or quotient group using the left coset of H in G. And this can be done only in that case. Theorem 9.2, let G be a group and let H be a normal subgroup of G. Then the set of all left cosets of G by H is a group under this operation. AH times BH is equal to ABH. So we use the operation in the group G to define the operation in the factor group. If the group G is with operation addition, then instead of AH, we'll write A plus H for the cosets. Example 10. Let for Z be the set of all multiples of 4. We construct the group Z factored by 4Z. So we have to consider the 4 cosets. Z has only 4 cosets with respect to the group, subgroup 4Z. For example, in this coset 3 plus 4Z, we have all the integers that have a remainder of 3 when divided by 4. because z with respect to addition is a billion, for z is normal, and the subgroup can be defined. And how we add two cosets, for example, 2 plus 4z plus 3 plus 4z will be 2 plus 3, 5 plus 4z, but 5 is in the 5 has remained the 1, not 4, so 5 is in this coset 1 plus 4z. That's why 2 plus 4z plus 3 plus 4z is equal to 1 plus 4z. So we can figure out easily from this table that z factored by 4z is isomorphic to the group Z4. Similarly, more general, if n is a positive integer, then z factored by nz is isomorphic to the group Zn. Example 11, let G be the group Z18. You know, here the elements are the numbers from 0 to 17, and the operation is addition, not 18. Let H be the cyclic subgroup generated by 6. This is the set of all multiples of 6 in Z18. So 0, 6, and 12. Then the factor group G by H will have how many elements? Each coset has 3 elements. How many cosets? 18 divided by 3. So we have 6 cosets. And one can check that all these cosets are different and disjoint. 0 plus h, 1 plus h, 2 plus h, 3 plus h, 4 plus h, and 5 plus h. Each of these will have exactly 3 numbers in it. To illustrate how group elements are combined, consider what is this sum, the sum of these two cosets. By definition, this is the coset that contains 5 plus 4. So it is 5 plus 4 plus h. That is 9 plus h. But here we don't have 9 plus h. This should be one of those 6 cosets. Which one? Just write 9 as 3 plus 6. And then 6 is absorbed by h. And we get 3 plus h. So 9 plus h is the same as 3 plus h. You can check this by writing the numbers that are included in this coset and the numbers included in this coset. It turns out that they are the same as sets of numbers. In a factor group, the meaning of this expression, AH, between vertical bars, can be different. There are two different meanings. One is if you consider this as a set, then AH between two vertical bars will mean the number of elements in the set. The other meaning is if you consider AH as an element in the factor group, then this will denote the order of that element. For example, in this factor group, from example 11, 3 plus h will have size 3 as a coset, since 3 plus h is this coset. We have 3 numbers, and as a group element, what is the order? We have to add the coset to itself until several times until we get 0. If we add 3 plus h and 3 plus h, we get 6 plus h, which is the subgroup H itself, and this is the 0 of the factor group. This means that the order of 3 plus h as an element in the factor group is 2, and this is the other meaning of 3 plus h between 2 vertical bars as an order of an element in the factor group. Now consider the part of example 14. Here G is U32. You know, here we have all numbers from 1 to 31 that are relatively prime to 32. So these are all odd integers because 32 is a power of 2. And H is selected to be this subgroup consisting of 1 and 17. This is actually the cyclic group generated by 17. Then G factored by H is an abelian group because U32 is abelian of order 16 divided by 2. We have 16 numbers here and 2 numbers in the subgroup H, so 16 divided by 2 is 8. This means that we'll have 8 different cosets, and one can see that these 8 cosets are different. It's obvious that they are disjoint, so they are different, and the union is U32. So these are all cosets. We can find the order of any coset as an element in the group. Here we have multiplicative notation, so we have to consider powers. 3h squared is by definition 3 times 3h, that is 9h, but 9h is different from h. 1h is h. 9h is different. You see those two sets are different. So the order of 3h is at least 4. Why is that? Because the order of any element is a divisor of the order of the group. And the factor group has order 8. So the order of any element must be 1, 2, 4, or 8. Since it is not 1 or 2, the order must be 4 or 8. It is at least 4. If you find 3h to the 4, it will be 9 squared. 9 squared mod 32. What is that? 9 squared is 81 minus 2 times 32, we get 17. This means that 81h is 17h, but 17h is the coset 117. That is, it is just h. This means that 3h to the 4 is equal to h. That is, 3h as an element in the factor group has order 4. You can try to find the order of some other element of the factor group. Example 15, we will consider this partially again. Let G be the group U32 and K be the cyclic group generated by 15. It consists of 2 elements only, because 15 squared is 1 mod 32. So the order of 15 in U32 is 2. Then the factor group has again order 8. 32 divided by 2 is 8. And what is the order of the element 3k in the factor group? 3k is one of the cosets. 3k squared is 9k, which is different from the subgroup. 3k to the 4 is 81k, and 81 mod 32 is 17, and 17k is different from k. You see, 17k contains 17, while k does not contain 17. 2 cosets are either equal or disjoint. So this cannot be equal. They must be different then. They are disjoint, for sure they are different. Which means that the order of 3k in this group, in this factor group, is not 4. So it must be 8 because it is a divisor of 8, as we know from the Lagrange's theorem. And you can check that if you raise 3k to the power 8, you will get k. Why the factor groups are important? When G is finite and H has more than one element, then the factor group is smaller than G, has less number of elements, and its structure is usually less complicated than that of G. At the same time, the factor group simulates G in many ways. It is because the operation in the factor group is defined using the operation of G. We can think that the factor group is a less complicated approximation of G. What makes factor groups important is that one can often deduce properties of G by examining the less complicated factor group instead. Example 16. A4 has no subgroup of order 6. A4, this is the alternating group. It consists of all even permutations on the set 1, 2, 3, 4. Assume that the operation is in this group is composition of bijections. Suppose that A4 does have a subgroup H of order 6. Since the index of H in A4 is 2, there are only 2 cosets of A4 with respect to H. It can be shown that H must be normal, and we can form a factor group. A4 by H, it has order 2, 6. 12 is the order of A4, 6 is the order of H. The quotient is 2. This means that any element of the factor group has order divisible by 2, so its square must be the unity of the factor group. That is, we must have this equality for any alpha in A4. Alpha H squared must be H, which means that alpha squared is in the subgroup for any alpha in A4. If we consider the multiplication table of A4, which is presented in table 5.1, then we see that there are 9 different elements of the form alpha squared, and each of them must belong to H, which has order 6, which is obviously impossible. So the assumption that A4 has a subgroup of H of order 6 cannot be true. And we prove the statement. A4 has no subgroup of order 6. Another application of factor group is this theorem 9.3. Let G be a group and let Z of G be the center of G. If G factored by ZG is cyclic, then G is abelian. Proof. Since G is abelian, is equivalent to ZG equals G. The center of G is equal to G. It suffices to show that the only element of the factor group is the identity coset, ZG. To this end, let G factored by ZG is this cyclic group, the cyclic group generated by a coset G times the center of G. And let A be any element of G. Then this is a coset from the factor group, but it is cyclic, so this coset is equal to some power of the generator. And that power is equal to G to the I times the center. This means that A is equal to G to the I times some element Z from the center. And now one can check that A times G is equal to G times A, because Z is in the center and both products are equal to G to the A plus 1 times Z. This means that G commutes with every element of G, that is, G is in the center of G. So G times the coset is equal to Z to the center. G times the center is equal to the center. That is, there is only one element in the factor group, which means that the center of the group is equal to the whole group.